Hello, everybody. We welcome you to the 9th National Seminar and 8th National School on Learning and Computational Intelligence, organized by the National Institute of Astrophysics, Optics, and Electronics, INAOE, the Conacyt Thematic Network on Applied Computational Intelligence, Red Temática, and the Systems Engineering Community of the National Tecnológico of Mexico, Campus Veracruz. Today, students, lecturers, and researchers, all interested on computational intelligence and learning, are attending this event to share recent findings in the area and establish collaboration links for future research projects and technological developments. We invite you to follow all talks live in Facebook and YouTube. For more information, you can visit the event official webpage at ccc.inaoe.mx/SNIKE/2021, where the complete program is available. All links will be available in the description of this video. We greatly appreciate the presence of Professor Tanya Mitrovic, who will share her experience related to new technologies and trends in computational intelligence, with the keynote talk, Artificial Intelligence in Education, Achievements and Challenges. As a reminder to all the audience, after the talk, we will have a Q&A session. So please write down your questions in the chat in English or in Spanish, and we will read them to the speaker. Now, I will give the floor to Dr. Yasmin Hernandez, who will read a brief resume of our speaker.
Thank you. Good afternoon, everyone. It's my pleasure to introduce our keynote speaker, Tanya Mitrovic. Professor Mitrovic will dictate the talk, Artificial Intelligence in Education, Achievement and Challenges. I am really excited to introduce her because I first met her excellent work on intelligent tutoring systems when I was a PhD student, and her work was very important in my research, since she is one of the most influential and dynamic researchers in this field. Dr. Tanya Mitrovic is a full professor at the Department of Computer Science and Software Engineering at the University of Canterbury in Christchurch, New Zealand. She is the leader of the Intelligent Computer Tutoring Group. Dr. Mitrovic received her PhD in computer science from the University of Nice in Yugoslavia in 1994. She is the president of the Asia Pacific Society for the Computers in Education and past president of the International Society for Artificial Intelligence in Education. She is an associate editor of the following journals: Intelligent Journal on Artificial Intelligence in Education, IEEE, Transactional Teaching and Learning Technologies, and Research and Practice in Technology-Enhanced Learning. She was awarded the Distinguished Researcher Award 11 by the Asia Pacific Society for Computers in Education. Dr. Mitrovic's primary research interests are in student modeling. Her research group has developed several constraint-based intelligent tutoring systems in a variety of domains, which have been thoroughly evaluated in real classrooms and proven to be highly effective. The system provides adaptive support for acquiring problem-solving skills and metacognitive skills. Also, most of the ITS developed by her group support student learning individually in areas such as database querying, database design, and database normalization. There are also constraint-based tutors for object-oriented software design and collaborative skills, several engineering topics, training on medical image interpretation and language learning. Her group has also developed a full authoring and deployment environment for constraint-based tutors. Recent research includes using personalized notes to improve engagement and learning outcomes in video-based learning. Please welcome Professor Mitrovic. Thank you, Professor, to be with us today.
Buenas tardes a todos. Gracias por invitarme. es un gran placer para mí hablar con ustedes hoy. And that's about the extent of my Spanish. So hello everyone from New Zealand. Thank you, Yasmin, for inviting me and for this nice introduction. I will now start my presentation. And I hope you can all see this. So AI in education, let me just tell you a little bit about how I started this. Back in 1989, I was a master's student and I did my master's at the University of Calgary in Canada. And I was taking a course on AI. I was really excited about AI and the promises of AI. And in that course, I heard about intelligent tutoring systems and I was just completely fascinated. I was a lecturer then and interested in AI, and that combination of AI and teaching was just the perfect combination for me. Now, if we look at some of the challenges and some of the promises, there are some estimates which say that in 40 or 50 years, there will be 10 billion human beings on Earth. And obviously, we want them all to have quality education. That's a very, very big challenge. So the challenges are, first, to support different types of learning. There are lots of different types of learning. So learning facts, learning to perform different motor skills like riding a bike or something like that, learning to solve problems in different areas and so on. But it's not only about different types of learning. We humans are all different as well. So how do we meet the needs of all learners? Learners differ in the amount of previous knowledge they have, in their skills, interests, age, cultural differences, and many other aspects as well. Technologies provide a lot of affordances. Obviously, it is possible to interact with computer-based environments. They also provide support for open-ended learner input. We can give feedback to the student, and this feedback can be adapted to the student's progress. We also allow non-linear access to the learner material and choice. Choice is very important, so we want the student to be in charge of their learning. And finally, communicating or collaborating with others, because that's now becoming more and more prevalent way of learning. So some examples of technology-based systems which support learning. We have instructional or serious games. You have all heard about MOOCs, massive open online courses, makerspaces, intelligent tutoring systems as one particular type, conversational agents, and there are lots of other types as well. Now, in my talk, I'm going to focus on intelligent tutoring systems. I know that some of you are already working in this area, but I have also heard that some people in the audience are undergraduate students. So I'm going to give a very short introduction to ITSs, and then I'll look at different ways of theories and different ways of representing knowledge, which we can use for ITSs. So intelligent tutoring systems are a type of educational software. They predominantly support learning by doing. So basically, that means that the student will get a problem and the student is working on the problem. The ITS is observing students' actions. And while doing that, the ITS will generate a model of students' knowledge. Of course, this model, which is known as the student model, is not perfect, but this is what the machine knows about the student at a particular point in time. ITSs use AI for different kinds of things, and I'm going to look into that a little bit as well. They use AI techniques to provide human tutor-like behavior. So the goal is to try to have a system which will behave in a way that a good human tutor behaves. So they have to be flexible, they have to be able to diagnose what the student is doing and adapt to the student as well. The classical architecture of intelligent tutoring systems consists of these four components. We have the interface, This is what the student sees, and obviously this is a crucial component. It has to be designed well so that it's clear, understandable, and easy to use. And at the same time, it has to support the student in specifying whatever they are learning, specifying different elements of the problem and solution. We have the expert model. So this is the component which contains the domain knowledge. This is what the student is about to learn. Then we have the student model, which I already mentioned. So this is the representation of the student's knowledge. And the pedagogical model, which decides on the instructional strategies and changes them over the course of time. Now, why do people develop ITSs? There are two reasons. The first one is the pedagogical reason. So we want to improve education. We want every single learner to have access to adaptive and effective environments. But there is also a scientific reason, and that's coming basically from educational psychology. We want to better understand the nature of human learning and teaching. Now, very, very briefly, a little bit of history. It is now widely believed that the first AI-based teaching system was Scholar, developed by Jaime Carbonell in 1970. It had some elements of AI. It had some elements of natural language understanding. And this system was teaching about the geography of South America. So in 70s and 80s, there were a lot of people who started working in this area. In UK, some of the famous names are John Self and Derek Sleeman. In the US, John Seeley Brown, Alan Collins, and of course, John Anderson from the Carnegie Mellon University. And based on their initial successes, this area became quite popular. And now we have people working on ITSs all over the world. It is an interdisciplinary field, so it obviously uses different techniques from artificial intelligence, but also from psychology, computer science, cognitive science, linguistics, education, human-computer interaction, statistics, and lots of other areas as well. An ITS has to reason about the domain. It also needs to reason about the learner, and the learner model is the source of information about the learner. It has to reason about the teaching strategies. So what is the best way to interact with the particular student, to give them feedback when they need feedback, and to help them overcome the impasses. And finally, the communication strategy. So this is about what is the actual way of communicating, which will be good for a particular student. I mentioned earlier the architecture. So we have several components which talk to each other. We have different places in the system where knowledge is stored. So we have the domain knowledge base, we have the set of student models, we have pedagogical expertise explicitly represented, and knowledge about communication. So this is the standard architecture. It doesn't mean that every single system has exactly this many components, but this is the widely accepted view on ITSs. So the domain model, as I said, that's the representation of the target knowledge, and it has two functions. It's the source of knowledge to teach, so this is what we want to teach the student, but it's also a standard for evaluating a student's performance. So when a student performs an action, we can compare the student's action to the domain module, to the knowledge that we have, and therefore we would know whether the student's action is correct or not. The student model, this is similar to user models which exist in other systems. And we have the model of students' knowledge, skills, and other characteristics. So cognitive skills, skills that are based on the domain level, but also metacognitive skills. Are they good in self-assessment? Are they good in explaining to themselves? Motivation, affect. So what is the affective state of the student? Because that can also have a big influence on learning, and engagement, and possibly other characteristics as well. The pedagogical module determines when to intervene, and what kind of instructional action to perform. Some of the pedagogical actions are diagnostic, so this is the process of analyzing students' work and seeing whether what the student has done is correct or not. And there are also didactic actions, so this is about what to tell the student and how to help them learn something new. Now, the interface, as I said, presents information to students, so it presents problems, feedbacks, and hints, and also accepts user actions. Now, in the last few years, there have been lots of meta-reviews of papers that present results of evaluating ITSs in different domains, and you can see some of them here. So on this particular graph, we have the effect size, so how much an ITS or AI-ed system improves learning on top of classroom teaching in comparison to the situation where we have a teacher and a set of students. So in each of these cases, the authors have analyzed a number of studies. For example, the first one, there were 66 studies that were compared. In the second one, we have 11 and so on. The average weighted mean of all of these studies show that there is an improvement of 0.47, so half a standard deviation. So that's half a letter grade. So that's how much, on average, AI systems improve learning in comparison to the classroom. However, there are systems which are much, much better than that. And there are ITSs that achieve 1 standard deviation or even higher, maybe even 2 standard deviation improvement in comparison to the classroom. Now, the next question we can ask is, what happens when we compare it to the human tutoring? Because we know that the expert human teacher is the best possible instructional situation. So when we compare AI systems to one-on-one learning with an expert human tutor, ITSs are still behind. So again, several kinds of comparisons, the weighted mean of minus 0.19, minus 0.2. So there is still a lot of space for improving ITSs. They have still not reached the effectiveness of expert human tutors. But there are lots of benefits. ITSs provide individualist support anytime, anywhere at the student's own pace. They allow us to collect data about how humans learn and to conduct empirical studies. They are cheap to use. Once when they are developed, you can use them as much as you want. But of course, they are expensive to develop. Generally, the maintenance costs are low. They can be extended and they're scalable and they use different kinds of technology. I have here screenshots from a few famous intelligent tutoring systems. This one is from Carnegie Mellon University. That's the cognitive tutor geometry, where you can see that the student is given the problem, they're given a diagram, and they can enter their solution step to step, and they get feedback from the tutor immediately. So whatever is shown in green, basically, that's the sign that the student has solved these parts of the problems correctly. The system can also give hints, so this is one of them. So this tutor is very, very popular and has been shown to improve learning significantly. Another one, this is Kurt van Lans and this tutor for physics, another famous system. So basically we have a problem, the diagram, the student enters the equations one by one, and the tutor will tell them whether that's correct or not and help them overcome problems as well. AutoTutor, this is one of the family of tutors developed by Art Gracer and his group at Memphis. So this is a system which is based on dialogue. So we have here the tutor presenting a statement. The sun exerts gravitational force on Earth, and Earth moves, and explain why. Okay, and then the tutor and student talk to each other. So the student would say something and then the tutor would provide feedback. So for example, here, the student's explanation is not perfect, so the tutor would provide a little bit of help and say kind of, but then help the student to focus on important concepts in the domain. So presentation of the question or problem, there's a talking head, an animated pedagogical agent which talks and performs different gestures, and then again inputs and the dialogue between the tutor and the student. Another very famous system, Betty's brain. So here the student is put in the role of a teacher, and the student is teaching Betty, an animated student, about something, and this teaching happens in the form of concept map. So the student explains different concepts in the area and how they interact with each other, and then from time to time the student can ask Betty to take a test, and then Mr. Davis, which is a tutor, will help resolve any inconsistencies in the model. Now there are lots of other systems as well. In a few minutes, I'll show you some of the systems that we have developed in my research group. But before that, let's look briefly at the fundamental issue, and that's how to represent knowledge. There are lots of different theories of learning, and all of them are specifying this distinction between declarative and procedural knowledge. Basically, the same piece of knowledge can be represented in different ways. And here we have one example. The first one says, the rightmost column is added first, then columns to the left, and if any column sums to more than 9, carry to the next. So this is a very short description of how multi-column addition is done, okay? This is basically the algorithm. Start from the rightmost column, add the figures in this column, and then move to the left. The second one is the declarative description. It says each column in 2-column addition is summed to produce a 2- or 3-column answer. It doesn't tell us how to do this. It just tells us what we are going to get as the result. So the result is going to be a 2- or 3-column answer. So these two pieces of knowledge have very different nature. The first one we can use to generate the actions, to actually add to numbers, while the first one is descriptive. It tells us when we are adding two numbers, we expect to get a number of this form. So why is this important? It is important because we do have right now ITSs that are based on declarative procedural. And the representation of knowledge, which is selected to be used in a particular ITS, will have an influence on other components of the ITS as well. So I'm sure you have heard about this, Newell and Simon's model of human problem solving. So we have the working memory, which is of limited capacity. We have declarative knowledge, we have procedural knowledge, and this procedural knowledge is represented in the form of production roles, where we have a specific goal and the current situation. And if these two parts are met, then we can perform action 1. And we can have a number of rules of this form. We get information from our sensory organs, and we can perform actions using our motor capabilities. So I mentioned earlier there are lots of different theories of learning that we can use. The two that are used widely are ECTAR, which is the basis of model tracing, knowledge tracing, and all the work that has been done at Carnegie Mellon University and elsewhere as well. And this is based on procedural knowledge. So we have domain knowledge represented as rules for solving problems in a particular domain. The other theory is the theory we use in my research group, that's learning from performance errors. It doesn't use procedural knowledge, it uses declarative knowledge. And declarative knowledge is represented in the form of constraints. And the student modeling approach that we use is constraint-based modeling. So I will now tell you a little bit more about this and then show you some examples of our systems. So in Hectare, as I said, they use production rules. They're generative, so you can use these rules to actually perform actions. And they have a set of correct and buggy rules in order to be able to see whether the student's action is correct or not. So basically, they match the student's action to the action that is generated using the domain model. In learning from performance errors, we use constraints, which are evaluative and we just represent correct knowledge. So let me tell you a little bit about this theory of learning from performance errors. It was postulated by Stellan Olson, an educational psychologist from the University of Illinois in Chicago in 1996. And in this theory, he looked at how people learn from errors, from their own errors. And there is a paradox here. And this paradox is about how can we detect our own errors. So if we do have the knowledge, then why are we making errors? And if we don't have the knowledge, then how is it possible that we can detect errors? And this theory says that people make mistakes when declarative knowledge is missing. So for example, we are new to a particular domain. We haven't learned much yet. Or the other possible situation is when we learned a little bit, but this declarative knowledge has not been integrated into the procedural knowledge. So the knowledge is still new and tentative, and that's why we make mistakes. Now, the other part of this theory talks about error correction. So how can we correct our faulty rule set when we know that we made an error? And basically, the theory says that both error detection and error correction are served by these constraints on good solution. So if we go back to the previous slide, if we are new to a particular domain and we try to solve a problem, it is possible that we are going to make a mistake because our knowledge is not perfect yet. However, if we do have declarative knowledge, we then know what type of outcome is a correct one or not. So the constraints represent features of correct solutions, and that allows us to identify errors we make ourselves. Now, if someone cannot detect the error on their own, then a human tutor or an ITS will help them to realize where the error is. And that's the basis of constraint-based modeling. So the applications of this theory for ITS design is to represent the domain in terms of constraints, so declarative knowledge, then to model the student again in terms of constraints, and for pedagogy, to augment students' constraint base. So this is a very high-level description, but I'll show you a little bit more in practical terms in a minute. So in 1992, Stellan wrote a very influential paper on constraint-based modeling, and that was at that time just a theoretical idea. There were no ITSs based on this approach. And he proposed this knowledge representation formalism known as constraints, where constraints encode domain principles. So the constraint is in general of this form. We have the relevance condition, and this relevance condition tells us when a particular constraint is relevant for the student's solution. And if the constraint is relevant, then the satisfaction condition, another part of the constraint, also needs to be true. Otherwise, the student solution is incorrect. So constraints of this form support judgment. So they tell us whether the student solution is correct or not, but they don't tell us how to actually solve the problem. So that's the difference from production rules. So let me give you a few example constraints just to see what I mean. So in New Zealand, you might know that in New Zealand, we drive on the left side of the road. So this is one constraint which describes this piece of declarative knowledge. And it says, if you're driving in New Zealand, so this is the relevance condition. you're in New Zealand and you're driving, then satisfaction condition, that's the second part. If you're driving, then you better be on the left side of the road, because if you're on the right side of the road, then obviously that's wrong. Another constraint, this is from mathematics. So the student is adding two fractions, and we have problems of type A over B plus C over D. A, B, C, and D are variables, so this will match lots of different problems. So the relevance part of this condition are the first two lines. So the student is solving a problem of this type, and the student solution is of this form. So the student solution is A plus C over N. Now, this constraint says that for the student solution to be correct, the only possible situation when that is so is when N equals B equals D. So basically that means these two fractions have the same denominator, and the student has added numerators. So that's only possible if B equals D equals N. Right? So by using these constraints, we can check the student solution and say whether they're correct or not. Now, typical ITS based on constraint-based modeling would have a large number of constraints. I'll show you in a minute one of them. The very first system we developed in my group is called Sql Tutor. That is the first constraint-based tutor ever, and it has more than 700 constraints. So it's a very large number, but the constraints have to be at a very specific level because of the advice that we can give to the student. I'll show you some examples of that in a moment too. So constraints-based modeling, basically we take the student solution, we match it to all the constraints we have in the system, and if there are violated constraints, then basically we know that the student made a mistake. If all constraints are satisfied, then the student solution is correct. Now, the short-term student model, so basically that's the model of the current situation, what the student has done. At any point in time, you might have a set of violated constraints and a set of satisfied constraints, and that's the model of that solution. There is no one-to-one mapping between problems and constraints because constraints are not problem specific. So they just describe knowledge in general. And you might have a problem which requires hundreds of constraints and a constraint that might be applicable or relevant to hundreds of problems. So when Stellan proposed this approach in 1992, he said, this is very efficient computationally, so you just need pattern matching. You don't need to have a problem solver. You don't need to represent student errors. The student can use whatever problem-solving strategy they want, and the system will still be able to follow what they're doing. It can be used with different kinds of pedagogical approaches. So, for example, you can follow the student step by step and give immediate feedback, or you can wait for the student to solve the problem or to ask for help and then evaluate their solutions. And it can deal both with well or ill-defined tasks. Now, as I said, at the time when Stellan wrote those papers, there were no constraint-based tutors. And I remember when I read this paper, I was really excited because this is such an elegant and simple approach. And I decided to start working on that. That was in 1995. So my group, Intelligent Computer Tutoring Group, some of the early work we have done was, the goal of that was to show that CBM works. Remember, at that time, there were no constraint-based tutors. So we wanted to show that it works to model different kinds of domains, to model students. We looked at different kinds of domains in terms of whether they are ill-defined or well-defined. So ill-defined tasks, some of the design tasks that we looked at include Sql Tutor, ER Tutor, JLatte, which is a tutor for Java, and other tutors as well. For procedural or well-defined tasks, we looked at a whole set of them. Here I just mentioned two of them, data normalization, thermodynamics, but we looked at lots of domains in accounting and business as well. Then we worked on how we can represent short or long-term student model and what kind of instructional decisions we can take based on CBM. So in terms of pedagogy, as I mentioned earlier, constraint-based tutors function by augmenting the student's own knowledge base. So basically what this means is that the ITS will help student identify the errors, and the ITS will also provide feedback to the student. So this feedback comes from violated constraints. Internal representation of the constraint always has, for each constraint, we have a number of feedback messages, and these messages which are attached to the constraints are then given to students when constraints are violated. And the feedback will basically tell the student which constraint was violated in terms of domain principle. So which domain principle is violated by the student solution and what they should do instead. So as I mentioned, the very first one was Sql Tutor. We had lots of different versions of it, and we performed more than 20 evaluation studies at the University of Canterbury, but also elsewhere. Then we worked on other tutors, and I'll show you some of them. This is Sql Tutor, and this time I'll give you a short demo of this system because it's going to be much more understandable once you see it in action. So I'll just log in. The version you're going to see now is the version that my students use at the moment. So there is a database course at the moment which uses this particular tutoring system. So we have had lots of different versions, but this is the current one. So when you log in, you'll see some information about the tutor. And this is the dashboard, which is telling me how much I have done this week. So this week I haven't used the tutor at all. I haven't solved any problems. And my current student level is 2. We have this student level as a measure of the student's progress, and it goes from 1 to 9. So my current student level is 2. And what you also see here is the student model, a visualization of the student model. Now, the student model in the system is something that you don't want to show to the student. It's too complicated for the student. So we just provide a visualization of it in terms of different parts of the select statement. The green part of the bar shows how much I have learned. The red parts are representing the mistakes I've made, and white parts means I haven't done anything on this, right? And we also have the numbers to show that. So this kind of visualization is very useful to encourage students to reflect on their knowledge, to do some self-assessment, and to do planning for their learning. Now let me go to the main space. In this system, we have a number of databases which serve as the context for problem solving. So if I go to the movies database, for example, and I can say, I want to practice the way clause, for example, and this is the list of problems defined for this database. I have previously solved this one. The system is suggesting to me to work on this problem. But as the student, I'm in charge. So we always put the student in the center. The student can override this suggestion and work on some other problem. So for example, I might want to work on this one. This is the main page of the system. And in the system, we show to the student the schema. This is the currently selected database, which has a number of tables. And for each of the tables, the student can see the attributes, and they can also click on this and see more information about what type of data is stored, and you can even see the real data in the table. Yep. So going back, this is my problem I need to solve. How many movies won more than 4 Academy Awards? So if you look at the movie table, we have this A1. So this is the number of awards won by a particular movie, the number of Academy Awards won. So in this case, Actually, I'm not going to enter the solution. I'm just going to submit it so that you can see. So if the student doesn't know how to start, they can submit an empty solution. And the system says there are 4 mistakes. If they still don't know what to do, they can submit it again and they will get a little bit more help. So it says there is a mistake in the select clause. And if I don't know what that means, I can submit it again. And it says the select clause is a mandatory one. Specify attributes or expressions you want to retrieve. Okay, so here we want to see how many movies won more than 4 awards. Now this is actually a little bit complicated, so I'll just going to do that. So we need to see, we need to use the movie table and we want the number of awards to be greater than 4. Now this is not the correct solution. It's only a partial solution. And if we submit it now, oh, it is done. Okay, so that's the correct solution. And I can go to the dashboard and now it's saying I have solved 1 of 5 problems and so on. I can change the goal for this week and that kind of stuff. So you have basically seen what happens in the system. So it leads the student, gives the student a little by little more information. And the student can progress and the student can set the goals for them. The other tutoring system I would like to show you very briefly is Tutor. This is again for the database course. And this is teaching them conceptual database design. So in this system, we have, again, a number of problems. The green ones are the ones I have solved before. They are ordered by complexity, and some of them, the later ones become very, very complicated. Like if I go into this one, you'll see that the schema can be very large. If I go into a simpler problem, basically what happens is that the student will start with an empty pane and they are supposed to design a database corresponding to the text. So in this database, we want to store information about composers. So composer is obviously something that's important. And composers have names and they have country they come from. So I'm defining different attributes and I can attach them to the composer. So we have this graphical editor. Now, the student can ask for feedback at any time. So for example, this is not the complete solution, but I can submit it now and the system will tell me there are some errors. And this part turned red. So basically this is a way to tell the student that there's something wrong with this. And if they submit it again, they say there's something wrong with entity types. If we want more help, it tells us that a regular entity type must have at least one key attribute, and we don't have a key. So it says here that there is a unique number. So this number is the key attribute. And I can put it here, evaluate it again, and now it says there are other mistakes. Some regular entity types are missing. So again, I should be defining compositions and the other parts of this problem. So again, we are giving step-by-step help to the student based on how they're working in the system. So back to the presentation. Sorry, skipped out of this. So that was Sql Tutor. We have done lots of studies in which we show that students are learning. So in terms of learning curves, the probability of making a mistake, the number of mistakes goes down regularly. This is one of the early systems as well in which we taught primary school kids, 9 to 10-year-olds, how to use capitals and punctuation in English. And they were given a piece of text and then they would add punctuation symbols. Again, it was very effective. I showed you Tutor, so I'll skip that one. This is a normie. This is for data normalization, which is a procedural task. Then we also had systems that teach elementary vocabulary, so type a word that matches the clue and so on. This is another example, and this was done for tertiary students. This is for pediatric students who are learning to diagnose diseases looking at X-rays. Now, a number of our systems were available on the database place from 2003 until 2016, and we had lots of students worldwide use them, and we collected a lot of useful data, which was actually marvelous for being able to improve the systems. Now, more recent work we are doing is looking at what kind of feedback, how do we phrase feedback to be effective? How do we support metacognitive skills? How do we support collaboration, affective modeling, authoring support? This is a combination of augmented reality and ITS. How do we do educational data mining and eye tracking and so on? So if it spend a minute talking about the feedback. So basically, we have done some studies which show that it is very important how you phrase feedback. And we use theory, that's the theory of learning from performance errors, to phrase feedback. We also now provide positive feedback to students. And we looked at relationship between spatial skills and what kind of feedback to present, whether it's visual feedback, which is best, or textual feedback. Now, when it comes to positive feedback, this was a very surprising study. We started from observing human tutors, and human tutors provide positive feedback a lot, while ITSs normally provide negative feedback or feedback on mistakes. So we wanted to provide some positive feedback, but of course you don't want to comment on every single positive correct action because that would be too much feedback. So we provide positive feedback when the student is uncertain. Basically, if the student made errors on a similar problem before and now they do it correctly, or if they were struggling with something and now they solve it correctly, or when they learn how to solve a difficult constraint or a difficult problem. Now, in the study that we performed, we found that the group of students who had positive feedback learned the same amount in half the time. So that's a very big increase in the speed of learning. And this is a screenshot of Sql Tutor showing that. So if you look at the feedback, the first part of feedback is positive. That's correct. You have specified all the necessary join conditions. So this is something the student was struggling in the past, but now they have done it correctly. But then after that, we provide negative feedback, and that's feedback on mistakes. Support and collaboration. So that was work of my PhD student. And she looked at how we can support groups of students working together. And how do we provide feedback on the domain level, but also provide feedback on collaboration. And this is a screenshot from that system. That's a system that teaches UML design. And here we have pairs of students working together. So the two students will get the same problem. And we ask them to work on the problem initially on their own. And this is that individual space. So the student starts solving the problem. After 10 minutes, they can see the group model and they start contributing pieces from their individual solution to the group solution. And the system is observing what they're doing and providing feedback on individual solution, but also providing feedback on collaboration. Now, to do that, we had a set of meta constraints that looked at how much students are contributing. Are they discussing enough? They had this chat area in which they could discuss their solutions. So we were looking at that as well and providing feedback. And again, we found that this collaborative feedback really improved collaboration for students who received that kind of feedback. So that's about the meta constraints. Then we have done some work on affect. So that is detecting the affect of the student and also having an animated agent which is capable of displaying affect. So this is an example from ER Tutor where the student has submitted a solution. There's some problems and the tutor is showing this concerned look. And that was also very interesting. We had different agents and the student could select the agent they wanted. And we were very surprised that our students wanted to work with female agents. They trusted female agents more, which was kind of unexpected in this project. Now, I mentioned earlier that developing intelligent tutoring systems is very expensive. You can imagine if you have a system that has 700 constraints, which have to be written manually, that takes a lot of time. So some of our work was on developing authoring systems, and we have Aspire, which is a system that helps the teacher develop a constraint-based tutor with no programming in some cases, or in other cases with minimal amounts of programming. So what happens is that we have the authoring side, and this is where the teacher can define the system, and then that's served on the tutoring side and students can use it. Now, to do that, it's a semi-automated process, so the teacher specifies some features of the domain, composes domain ontology, which is very simple, specifies the structure for problems and solutions, and then the rest of the steps are performed automatically. This is too much for the talk today, so I'm not going to go into details, but if anyone is interested, I'll be very happy to give you more information and to give access to all these systems as well. These are some of the systems we developed in Aspire, and our experience shows that it is still not completely automatic, so there is some work. It depends on the domain that you want your ITS to develop in. So in some cases, our teachers were able to develop the tutor completely on their own, and in some other systems, we had to help them with some bits of it. This is a screenshot from one of them. This is the system for thermodynamics, where the student gets a problem, they develop the graph, and then they fill the tables and they get feedback from the system. This is another one. This system was developed again for tertiary students. These are students who were learning to be radiographers. So in this particular case, they get X-rays, and their task is to say whether these X-rays are good or not, and if they are not good, to say how the parameters on the actual machine has to be changed so that they get a good X-ray image. There were lots of other projects as well. Some of the more recent projects, we are now using eye tracking a lot to investigate how students use our systems, how they, whether they understand the open student models, the visualization of the student models. We are looking at supporting multiple instructional strategies, such as using not only problem solving, but also worked examples or erroneous examples, using EEG data for effective modeling. We have even used constraints in working with stroke survivors. This particular project was about teaching them how to improve their prospective memory. Basically, that's memorizing what they need to do in the future. I mentioned open learner models, and we have done lots of different types. So these are some of them. And we have done eye tracking studies to see which types of models students prefer and whether they're understandable as well. And let me spend just a few minutes on the current project. I'm really excited about this project. We recently got a grant from the New Zealand Ministry of Business. So a few years ago, I started working on this with Professor Tanya Mitrovic from the University of Leeds in the UK. What we were interested in is, after having all this experience in teaching hard skills, can we also teach soft skills? Soft skills are crucial for success in learning and also in life. So we wanted to see whether we could find a way to teach soft skills. Now, both of us are in computer science departments. And when we started thinking about which soft skill to focus on, the first one we selected was presentation skills. Our students find it quite difficult to give presentations. So that's the first soft skill we decided to work on. And at the moment, we are conducting a study on a different skill, which is aimed at software engineering students, especially how to behave in face-to-face team meetings, software development meetings, which are held face-to-face. So we developed this platform called AVW Space. AVW stands for Active Video Watching. So this is video-based learning, but we use AI to provide support to students to become engaged in learning, because this is one of the basic problems with video-based learning. It's so easy to just passively watch the video and not learn much. So our AI-based support aims to engage the student, to make them think, to reflect on their knowledge, to reflect on what they have heard in the video, and to plan for future. So AVW Space has two phases. There's the personal space and the social space. And this is the screenshot, but I'm going to give you a short demo of that instead. So if I go into AVW Space, this is the system, the version of the system which is currently used in our second year software engineering course. So here again, see that we give a survey to the students at the beginning. There is a number of videos, and we are telling them how many they have watched. Now, this is my account, so this is not a real student. We are showing to them how many videos they commented on, how many comments they rated, and finally survey 2. So some of these videos are tutorials. All these videos are from YouTube. So these are publicly available videos that we selected for students to watch. And you can also see that I have watched some of the videos, but not all of them. So for example, if I go into this video, at the beginning, we tell them something. Now, I have watched this video before. I have written some comments. You can see the comments I made previously. What you see here is a nudge. So this is the AI-based intervention that we developed based on my behavior in this particular video. So I have watched the video and I have made some of the aspects, and you can see the quality. So we have machine learning classifiers which online, as the students write comments, these classifiers will analyze comments and say what is the quality. So in this particular case, quality is 1. That's red, so that's low quality because I just wrote nice. So this is not a comment which tells the system that the student is really thinking about what's happening. Or like this one, Now, when they write comments, if I start this video and I want to write, if I want to write a comment, I have to stop it, and then I can say something about I like this video or whatever. Now, when they write comments, they also have to select one of these aspects. And if you look at the aspects, they're defined so to encourage the student to think about their experience. So I'm rather good at this, or I did or saw this in the past, or I didn't realize, or for example, this is something new I learned, or I like this point and I can save it. And I'll just stop the video. So the comment now appears. Now these things are nudges that I have received in the past. So there was a nudge which says this is vague. Can you elaborate more? Or this nudge which says try to elaborate more, challenge ideas, that kind of stuff. So this is the kind of support we are providing to them. And also we have these visualizations. So these are examples of good comments written on this video from previous students. And the student can mouse over a particular comment and see the text. Now I'll just show you very briefly the social phase. In the social phase, they can see each other comments and they can rate them, so they can read what other people have written and they can say, this is very useful for me or whatever. So that's the kind of support we provide. And we use constraint-based modeling basically to generate these nudges, which I showed you. So basically, there's a few more examples of the nudges. The studies that we have performed so far, we have performed 15 studies with AVW space, mostly with presentation skills, but with different types of students. And we have seen that students who write comments and who rate comments written by others learn much more than other students. So the more engaged they are, the more they're going to learn. The current study that we are doing with software engineering students, there's one other phase at the end in which we actually record their own meeting. So then they can watch themselves in the meeting and they can comment on their behavior. And that was a lot of fun because they write things like, I remember one comment was like, if I saw someone behaving the way I behaved in this meeting, I would think that that person is completely bored or something like that. So they're reflecting on their own behavior and how they contribute to meetings. I'm out of time, so I'll stop here and just invite you to email me if you would like to try any of our systems. And thank you for your attention.
Thank you, Professor, for your interesting talk. We have some questions for the audience. I am going to read them for you. Luis Avila asked you, what is the most problematic thing about AI versus classroom teaching? Isn't it a great problem, the human side? Is the human side a problem?
If we are comparing an AI system to the classroom, I'm not actually sure what this question means. So basically, the advantages of having AI systems in comparison to the classroom. If you have one teacher in a classroom and say 30 students, obviously the teacher cannot devote enough time and attention to every single student. So when we teach a large group of students, we aimed at an average student, while the AI system will analyze each student's actions separately and can provide tailored feedback. So the AI system will know what the main principles the student has problems with and will provide tailored feedback to that. Now, the human side, as I said earlier, the best instructional setting would be one student working with one expert teacher. Okay, so we have the teacher who is very good in the particular domain, but the teacher who is also very good in teaching. And AI systems are not at that level yet, but they are definitely much better than classroom teaching.
Thank you. Jack Martinez asked you, how did you interested in this field in particular, in ITS?
So as I mentioned earlier, when I was the master student, I was working, my master thesis was about machine learning. But then I heard about intelligent tutoring systems and I was thinking, this is really exciting. Can we have computer systems that teach well and can be adapted to each individual student? So that was my original motivation. That was like more than 30 years ago, and I'm still very excited about this area.
Thank you. Also, Jack Martinez asks you, what do you advise to interested students who wants to study in this field?
Well, there is a lot of space for research. I mentioned some of them during the talk. If someone wanted to do, say, a PhD in this area, I don't think it's a good idea to have the goal of developing a completely new ITS. because that takes a lot of time and a lot of effort. Probably the best solution would be to find a group which already has intelligent tutoring systems, and then you try to improve one component and you measure the improvement on that one component on top of the existing system. So I have several students at the moment. Some of them are looking at, some of them are doing educational data mining, so analyzing the data we collected from previous studies, finding some problems that students have, and then thinking about how can we overcome that. Like, for example, you might have students who become bored during learning. So what kind of intervention can we take for them? How do we keep them engaged? And that was also illustrated in this example of AVW space, where we see if there is a student who is just passively watching videos, not writing anything, we give them these nudges, these hints, trying to make them think about the material deeper, and that results in better learning. So I think if someone is interested in this kind of work, probably find a group, research group that already has some systems, and then think about some of the existing problems. There is a lot of work at the moment on natural language, using natural language for teaching. There is obviously a lot of work on deep learning. Deep learning is so popular at the moment. So looking at how deep learning can be used with intelligent tutoring systems. There are also lots of different projects which look at underrepresented student groups who don't learn as much as other students. Like, for example, one of my PhD students has recently analyzed data from AVW space, especially looking at domestic students, so students for whom English is the native language, in comparison to international students. And we have seen a lot of differences. So international students learn less, they write fewer comments, and there could be lots of different reasons for that. One obvious reason is that they might be struggling with English, but other reasons might be cultural. In some cultures, students are not so willing to openly present their opinions. So we are now thinking about how can we change the system to be more welcoming to international students.
Thank you. Diana Hernandez asks you, what do you think about the roadmap on intelligence, on artificial intelligence in education and the required skill in students?
I think there is a lot of potential for AI ed. You have seen from a brief history that the original work started in the 1970s. But until recently, many people didn't even know that something like AI ed exists. Now it's becoming more popular, but it's still not widely used. And there are several reasons for that. One of them is that these systems take a lot of time to develop. Luckily, nowadays we have some authoring systems available, so it's becoming easier to develop these systems. There are also other approaches which I haven't mentioned, like crowdsourcing, that kind of stuff. So reusing some of the components. But there is definitely a lot of space for further impact. In the US, for example, there are several systems which are widely used in high schools, some of them from Carnegie Mellon University. So Carnegie Learning is a spin-off company which started from there. But there are also others like Neil Hefernan's assessment, which is used in many, many high schools to help students learn mathematics. So they are becoming more visible, but there is still a lot of space for further improvement and for popularizing these systems more, because we know that they work. We have evidence that they work. Now, the second part of that question was about the skills. Obviously, you need to know about computer science, right? You need to know about AI. But there is so many different types of projects in this area that not all of them would require programming. Not all of them would require specific type of techniques. There are also projects that can involve students who are interested in design, especially when it comes to designing interfaces, designing open learner models. So how do we visualize the student model to students and that kind of stuff. So there are lots of different techniques. Not everyone has to have all types of knowledge, but obviously if you're in a larger group, then there would be other people with complementary skills. Something that is very important is also statistics and data science, that kind of skills. When you evaluate systems, you need to be able to apply different types of analysis in order to understand whether students learned successfully or not.
Thank you. Ivan Okrasia asks you, could you imagine some negative repercussion or impacts it could lead this technology from a social perspective?
Of course, everything can go wrong, right? We have the best intentions when we develop these systems, but it doesn't mean that they would suit every single user, every single learner. Something that comes to my mind immediately is about cultural differences. And we have seen a lot of that already. We know that in some cultures, as I said earlier, students have a lot of respect for the teacher and they would never disagree with the teacher. They would not openly present their opinions. While in other cultures, that's perfectly fine. There are also differences in terms of affect, for example. In some of the cultures, especially, for example, Japan, people don't show facial expressions so much as in other countries. So, for example, if you go with that type of research, affective research, that could be an issue. But at the moment, there is also a lot of work being done on privacy. So how much we have to take privacy of student data into account. And there is a lot of work also on explainability. So we should be able, our systems should be able to explain to the student why their student model is like this. So what is the evidence, for example, to say that someone doesn't know a particular part of the domain, or how the system recommends a particular problem. I didn't show you that, but our systems can select a problem for the student based on the student model. So based on the current state of student's knowledge, how do we actually select the best problems for the student? And the student should be able to say, well, why did they get this problem and not something else? So there are those types of issues that are being done. A lot of work is being done on them at the moment.
Thank you. And the last question is from Fernando Samir Salas. What will happen if instead of positive comments, the student receive negative comments when making constraints?
I assume that's a question about positive and negative feedback. As I said, most ITSs provide negative feedback. So that's feedback on errors. The current situation in schools especially is that teachers provide more positive feedback than negative feedback. However, as I talked about earlier, theoretical foundations say that in order to learn, you have to get negative feedback. If no one tells you that you made an error and why that error is important and how you can correct it, you will in some cases not be able to learn something. So we need to have negative feedback as well. There is an issue here. Some students react more dramatically to negative feedback, so they might be upset if they get negative feedback. So there must be a balance in how we do that, and that's something that is still open for research. I don't think there is much done on that level. You know, what kind of feedback to give to the student if we know that the student gets anxious or stressed by receiving feedback from the tutoring system.
Thank you. We would like to continue listening to you, Professor Mitrovic, but we will most close at this point. Thank you to be with us today. We are very, very grateful to you for making this talk possible, and we would love to have you in future events from the Red ICA, hopefully in person. Thank you.
Thank you for your attention. And just to iterate, if anyone is interested in using our systems, please let me know. We would be very interested to hear your opinions. And if anyone is interested in collaboration, I would like to hear from you. Thank you very much.
Thank you. See you soon.